recording. So today we'll have our last lecture. Next time on Monday we'll go through hopefully two, but definitely at least one old exam. And I hope by Monday I'll more or less decide what kind of written exam you'll have in January. So those old exams are available from the web page together with their solutions. So if you have time, please take a look. And in general, if you have any serious questions, but about the course itself, not about what I would get on my exam in January, this I cannot answer you now. But about the contents of the course, please either mail me or maybe save it till we meet on Monday. Okay, so today we should talk about so-called finite geometries and leading squares. So before we start this is a small separate portion, very nice, of our course. So last time we were discussing optimization still, and also a very nice and beautiful part of graph theory, which is related to flows in transport networks. And transport network is a directed graph, weighted directed graph, with the following properties: that it has one source and one sink. In other words, one vertex, it should be connected. One vertex where all edges are directed towards this vertex called the sink, and one a vertex where all edges are directed from this vertex, which is called the source. And so the idea is that a flow is a assignment of positive numbers to the edges, such that except for the sink and the source, there is a balancing condition at each vertex, meaning that all inflows added together should be equal to the total inflow to any vertex except for the sink and the source should be equal to the total outflow. So the general flow through any vertex except the sink and the source should be zero, which is a natural thing in practice, of course. And the optimization problem is we have weights or capacities, they are called, which are in this case also positive integers, and we want to maximize the total flow. And the total flow is what goes out from the source, or equally one can easily show that that's the same number which goes in the sink. And this total flow can be also calculated using any so-called cut. And the cut is just a separation of vertices into two disjoint subsets, one containing the source and another containing the sink. And the famous result by Ford and Fulkerson says that the maximal flow equals the minimal cut, where the size of the cut is the capacity of the cut is, so if we separate our set of vertices into two disjoint sets containing the source and the sink, so we count all vertices, we add up all capacities of all edges going from the first part containing the source to the second part containing the sink. And the minimum over all of these numbers over all such cuts equals the maximal possible flow in a network. Okay, now today we'll be discussing our last topic. As I mentioned, let me share the screen. It's not related to optimization. It's a very nice topic related to combinatorics. It's quite algebraic. It's related to the so-called finite fields, and also to Latin squares. Maybe you have heard about those. It's a nice matrix gadget, which is kind of resembles Sudoku, in fact. Okay, so I start, you hope you see my screen and you hear me. I start with the definition of an affine plane. Finite affine plane. So the motivation for this notion comes from the usual plane in Euclidean, Euclidean axioms. We want to mimic using finitely many points and lines what we know for the usual plane, and which comes from Euclid. And Euclid's axiom says that so if we take two distinct points in the plane, there is a unique line passing through them. So you have a line and a point not on the line. There exists a unique line parallel to a given one, and parallel means not intersecting. So we say that two distinct lines are parallel if they do not intersect each other. That's of course obvious in the Euclidean geometry. And finally, the last thing which we'll need is that well, the last thing is probably not so natural in the usual Euclidean geometry, but it's important for the finite affine plane. So let me list the axioms of the finite affine plane. So a finite affine plane is a pair consisting of two sets P, which would be a finite set, and L. So P stands for points, and this guy L stands for lines. So P is a finite set. L consists of subsets of P, such that, so we have to, certain axioms has to be satisfied. So first of all, for any pair P not equal to Q in P, so there exists a unique line L in the set of lines such that it contains P and Q. This is our first axiom. Our second axiom would be for any line L and any P, point P, which is not on the line, so there exists a unique line L prime in L, such that first of all it contains P, L prime contains P, and it does not intersect L. The intersection of L and L prime is empty. And the last axiom, it's called the non-degeneracy condition. So there exist 4 points, P1, P2, P3, P4 in P, such that any line in L contains at most 2 of them. So this is the axioms of the finite plane. Let me start with some examples. I'll repeat these axioms several times. Okay, so
could you keep the previous in frame just so yeah.
okay, so I'll still have some space here. One example. This is the simplest or the smallest affine plane. It consists of 4 points and 6 lines. So these are the points. And the lines are all possible pairs of points. 1, 2, 3, 4, 5, 6. So this configuration is the simplest possible non-trivial finite plane. So it satisfies all the axioms. So so what do we check? So we check that for any P and Q, for any 2 points, there exists a line. Yes, this is true in this case. For any line and any point not in the line, there exists a parallel line. This is also true here. And finally, so we just have 4 points in this configuration, and no line contains more than 2 of them. So this is also true. So all 3 axioms are satisfied in this toy example. Now, another example, more general thing, would be related to the so-called finite fields. So this would be example 1. So I have to move, but I'll recall. So example 2, affine planes of finite fields. Let me recall briefly. Hopefully you know what a finite field is. So a finite field is the following thing. So if Q is a prime number or a power of prime number, so first of all, finite fields. Finite fields. So for any, say, prime number, number Q, the set Z mod Q, so which contains, you hopefully know what this thing is, yes? So it contains numbers 1, 2, 3, and so on to Q minus 1, with the addition and multiplication inherited from Z, is a field. What does it mean? Well, that means that you cannot just add and multiply its elements. You probably remember this from modular calculus, this construction. But you can also invert any element except for 0. So it satisfies all the axioms of real numbers or rational numbers or whatever field you are more familiar with, complex numbers. So this is a finite field where the number of elements is a prime number. There is also a generalization of this notion when the number of elements is a power of a prime. For example, there is a field with 9 elements or 27 elements. This I cannot go into more details about in any case for any prime number q and any its power q power l, there exists a unique finite field containing exactly that many elements. And if q itself is a prime number, then z mod q is, which is obtained by taking integers and taking their modular classes mod q, will be a field. Okay, after recalling this, now let me go back and define what an affine plane over a finite field is. So if f is a finite field, finite field, so we can define the affine plane the affine plane, so call it capital A with index f, as just the Cartesian product of f times f's. And now I'll define the set of lines L as follows. So points would be just pairs of elements in the prime field. So it's just the usual Cartesian square. Now, what about the lines? So the lines would be of two different kinds. So lines will, the set of lines will have will be the union of lines of the form A and B, where A and B are elements in the field. So this would be one type. And then there will be another type, L of just one single element A, where L is an element in our field. Okay, what is LAB? LAB, so we're fixing two numbers in our finite field, and we're looking at the set of solutions. So let me denote this by f square, which is just a Cartesian product, such that ax plus b equals y. So just the set of solutions, of, if you want, of all lines which have a positive slope, which have non-vanish, let's see, which are not vertical in the usual sense. And LA would be the set of lines, the set of points in f squared such that x equals a. So these are vertical lines in the usual sense, and these are non-vertical. Okay. Now I want to show that the set of the Cartesian product of f with itself, with the set of lines defined like this, will satisfy all our axioms. So proof. So why is this a finite plane, finite affine plane in our usual sense? So what do we need to show? So we need to show three axioms, yes. So through any two distinct points, there exists a unique line. This is the first thing. B, for any line and the point not on it. So line L, say point P, P not on L, so there exists a unique L prime such that it does not intersect L. And finally, the last thing is there exist 4 points such that no line hits them in more than two. More than two, yes. Okay, so let's do this one at a time. Okay, so for any points, there exists a unique line through them. So part A. So if we have 2 points, say they have coordinates x1, okay. So let's see.
Sorry, can I ask a question? What's the difference between exist and exist utropstecken?
Well, this is exist and unique.
Okay.
So this is exist and unique. It's also the standard notation. Existence in general does not apply any uniqueness, of course. Yeah. Two. Okay. So okay. So say we have 2 points x0, y0, and x1, y1 in F2. So which are not the same. So when we have this, now we check. So there are 2 subcases. Case 1, x0 equals x1. Then take L equal to whatever given by x equals to x0. Yes. So if we look at the line of the type, the second type, such that the x coordinate is a given number, then it contains both points, of course. Now, if x0 is not x2, x1, then we can take the line with the slope, which would be then given by take L of the following kind: 1 y1 divided by x1 minus x0 and y0. So this line, if this is taken as A and this is taken as B, so this would be the slope, and this would be, this shift over the origin. So this line will exactly contain both points. If we substitute it here, we'll see that coordinates of both points satisfy the equation. Okay. Now the second thing is to show that if we have a line and a point, then there exists another line parallel, not intersecting, not intersecting the first one. Okay, again, we have to consider 2 cases. In the first case, say L is given by x equals to some number. So this is of the second type. And for P is of the form A prime, B prime, where this is not A. Then the line we are looking for would be then take L given by L, this L prime given by x equal to A prime. So we take a vertical line and which passes through our point P, and this is definitely parallel. It's not intersecting the first line L. And case 2, so if we have LAB, this line is LAB, so it is given by, what do we have? LX plus B equals Y. And say P is not there, does not satisfy this equation. Then we'll have to take L prime given by, so we have to keep the slope, of course, AX, and here we have to, let's see, we want our point P. Let us give it some coordinates, say UV. We want it to satisfy this equation. So what kind of shift do we need to put here? So we have AU plus our new shift B prime equals V, and that means that B prime should be V minus AU. Okay, so I have to put here V minus AU. And that's, again, if we check these two equations, they do not have any common solutions. Okay, and finally, the last part C is we need to find 4 points such that no lines in our list of the lines would hit them at most twice. So that's a nice thing. Take 4 points of the form. So in our field, we have element 0 and we have elements 1, of course. So if we take 0, 0, 0, 1, 1, 0, and finally 1, 1, then yeah, let me skip this. It is easy to check that no line in our list contains more than 2 of them. Yeah, so the picture actually looks like the one I just started with. So either, yeah, so all interesting lines which contain at least 2 of them will be those guys. So these will be the lines containing 2 of them. There will be exactly 6 of them. And the rest of the lines would contain 1 or no points among those. So if we just plug this in the equation, so how to check it? Say, so we can look at, say, if we look at lines containing, for example, 0, 0 and 0, 1. They should definitely be of the form x equal to 0. So they will be not containing 2 other points. And similarly, if we look at lines which contain 1, 0 and 1, 1, there can be only one such line, x equal to 1, and it contains no 2 other points. Similarly, the horizontal line we should check. And now we have to look at lines containing, for example, 0, 0 and 1, 1. So these are lines of the form x equal to y. Yeah, there is just, again, one such line, and it's not containing 2 other points. And the other way around, if we have, if we look at all lines containing 0, 1 and 1, 0, this is the line of the form x plus y equals 1, and it's unique and it does not contain any other points. So it's a fairly easy, straightforward exercise to check that these 4 points chosen like this, they satisfy the third axiom which we impose on affine finite planes. Okay, good. Now let me give you an example how this looks for in the case when we have a field of 3 elements. Okay. So affine plane over the field F3. So it's in your book. So I'm not sure I'll draw the best picture possible, but still. So we have elements in our field are just 0, 1, and 2. And we take its Cartesian square. So we have now 9 points here, 0, 0, 0, 1, 1, 0, 2, 0, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. These are our elements in our field. Now, what are the lines? And we'll have, in this case, 12 lines. We'll show, so we'll after some 10 minutes, prove the important result, saying that in a affine finite plane, the number of points is a square of an integer, and the number of lines, say if this integer is n, which is called the rank of the affine plane, then the number of lines would be n squared plus n. If n is 3, as in this case, then the number of lines would be 12, and let me show them. So we have 1, 2, 3, 4, 5, 6 lines. Then we have 7, 8, and we need another 3. We need another 4. One line would be like this. These two guys, and this would be one line. Then we have similar things. So we'll have, let's see, this and that. And we have going this way. So this would be this guy and that. And finally, one more is missing, this and that. So 9 points, 12 lines. Okay, so that's the first non-trivial example showing how points and lines can be arranged in a finite affine plane. So let me go further with the next definition, which is natural in this situation. So given a finite affine plane, say X consisting of P and L.
Can I ask a short question?
Sure, yes.
Could a line go through 2, 0, and then 1, 0, 2, 1, for example?
2,
No.
2, 0.
So the top
okay.
left, then
Yes.
the one diagonal line to the right.
One diagonal. This one, no?
No. So
2,
top
0,
left,
and then which one?
and then down one step.
1, 0. This one, no?
No, 1, 0 is to the left.
Okay, so tell me the numbers. 2, 0, and
Yeah.
which,
Okay. So
which,
2, 0, 1, 0, 2, 1, as you written them.
2, 0, 1, 0.
Yes.
And then
2, 1.
2, 1. No, there is no such line. No.
Okay. So which rule does that?
Well, we'll see that the axioms would. Okay. I'll soon tell you the classification, kind of the basic classification result. And then maybe it would be a good exercise if you try to plane that if you add what you want, a subset with these 3 points, then it will spoil the axioms. Yeah. Well,
Okay, thank you.
so I'll give you the major classification result, and this will explain why. I mean, so yeah, how should I say? So the labeling of points in this situation is kind of canonical, and then you can figure out. I mean, what you suggest will not satisfy a linear equation. So lines should satisfy either an equation x equals to a constant, which are those 3 vertical lines, yes? Or they should satisfy an equation ax plus b equals to y. And you are suggesting which? 2, 0, 1 point? Then you want 1, 0, yes? And then you want 2, 1? Is it like this?
Yes.
Yes, but then they do not lie on any line like this. These first 2 lie on the vertical line, x equals to 0, and this does not. So it's a quite rigid thing. Well, maybe I should go further. If you want, you can maybe mail me and we can discuss it separately. I don't quite have time now. But so in this affine planes of a field, so we're really looking at Cartesian product of 2 copies of our field, and they're looking at linear equations. And our lines would be pairs of elements of finite field which satisfy linear equations. And what you are suggesting is not satisfying, this triple of points is not satisfying any linear equation. Okay, so
Thank you.
again, please, if you want to discuss it more, contact me after maybe. Okay, given an affine plane, we say that 2 lines are parallel. 2 lines are parallel. Too many L's. I don't know which is wrong. If they either coincide or do not intersect. It's just the usual notion of intersect. So it would be convenient for us to say that 2 coinciding lines are still parallel. That's not such a big deal. Okay, now a small lemma says that being parallel is an equivalence relation among lines. Being parallel is an equivalence relation among lines. What does it mean? Well, it means, so first a line, so it's symmetric. So every line is parallel to itself. If a line A, so L is parallel to itself. And the second one is if L is parallel to, I don't know, L prime, then the other way around, L prime is parallel to L. This is also obvious. So if 2 lines coincide, then there is no big deal. If two lines do not intersect, then it doesn't play any role which of them is the first one, which is the second one. And finally, the third one is the transitivity. If L is parallel to L prime and L prime is parallel to L double prime, then L double prime is parallel to L. This is also an easy thing. Okay, now using this, so a small conclusion, split all lines in our finite field. Oh, sorry, what did I say? Our affine plane into, this is called parallel classes. How they are called? Parallelity classes, into parallelity classes. So we split all lines into pairwise parallel to each other lines. Okay. Now the following key theorem is important. So this is really a major theorem here in this area. So for any finite affine plane X, which consists of points and lines, there exist some positive integer n bigger or equal than 2, such that the following holds. So first, every line contains n points. Every point is contained in n+1 lines. So there are n+1 parallelity classes. And okay, so there exist exactly n squared plus n different lines. And finally, there exist exactly n square points. In X. So it's a very rigid construction saying every affine line contains a square number of points. There exists a number n, so it contains of n square points, n square plus n different lines. They are which split into parallelity classes, n+1 parallelity classes, and each line has n points. Each point is contained in n+1 lines. Okay, so we'll prove it in a second. So n is called the rank. That's an important notion of X. And now here is, there are different finite planes with a given rank. You shouldn't think that for a given n, so first of all, there are major open questions, open problems. As far as I know, maybe there were some recent advances which I don't know of, but so for which integer n there exists a finite plane of rank n. I think this is still not known. So by the end of the lecture, we'll kind of motivate using Latin squares that n = 6 is impossible. But I think in general it's an open question. So we know that for prime, for power, for n, which is a prime number, such planes exist, which is a power of prime, such plane exists. So the first non-trivial number, which is not a power of a prime, is 6. So 2 is a prime, 3 is a prime, 4 is 2 squared is a power of prime, 5 is a prime, and 6 is the first number which is not like this. And for 6, there is no rank equal to 6 is impossible. And as I said, I think there is no knowledge for which n, complete knowledge for which n this is impossible. There are big classes of n for which it's known that finite fields exist, and big classes for which it's not, for which is known that they do not. But in general, I think the answer is still unknown. And maybe let me make a break now because it's a good point. So and then we continue with the proof, and I'll tell you some few details about Latin squares. Okay, good. So let me make a small pause, and we continue in 10 minutes. Good. Okay, so let's see. So not quite sure. We make another try to share the screen. Okay, good. Yeah. So I hope you're here. And I guess, what about my recording? Does it continue? Yeah, recording is on.
Boris, just a short question about
Yeah.
affine plane. So, so this ax plus b equals y. It's usually when we have used it earlier, we used it for a straight line, and in affine plane, it's not necessarily a straight line. Is it about modulus for a modulus n for a, b, and y, which makes it possible to actually bend?
Okay, so a and b are fixed elements in our finite field. For example, in F mod 11. And x and y are also considered as variables, also with values in our finite field. So we are solving this linear equation, which looks like a usual one, but both a and b are fixed elements in the finite field, and x and y are variables taking values in the finite field. That's what we are doing.
Okay, thank you.
Okay, good. So let me continue. So let me repeat our major theorem, and then we'll continue with the proof. So we are claiming that for any finite affine plane, there exists a positive integer n, at least 2, such that the number of points is n squared, the number of lines is n squared plus n. Every line is an n points, every point is an n plus 1 lines, and there are n plus 1 parallelity classes of lines. Okay, so let us start proving that. Okay, and here how it goes. Let's see, do we need one additional lemma? So extra lemma first, not very difficult. So there exist at least 3 distinct parallelity classes. Classes in any affine plane. Affine plane X. Okay, and the proof, so the proof is as follows. So we use the third axiom. So there exist 4 points, P1, P2, P3, P4 in the set of points P, such that no line contains more than 2. Now take 3 lines, L1, which is passing through P1 and P2, L2 passing through P1 and P3, P1 and P2 and P3, and P3 passing through P1 and P4. And the claim is, these 3 lines cannot be parallel, It's not very complicated to show, in fact, and I'll jump over it. And so if we're looking at these 3 lines, so, and they should lie in separate parallelity classes always. And that means that for whatever affine plane we take, then we have at least 3 parallelity classes. So we'll need this additional statement in our proof of the general statement. And it's not very difficult. If you take a look, you can see that since they pass through one and the same point, if they were parallel, they should coincide, but they cannot coincide. So it's a simple statement. Okay, with this lemma, we can go further and try to prove our major results. Okay. So proof of the main theorem. So we need one additional claim here, which is a part of the proof, or maybe a separate statement. So let X PL be an affine line. Now fix some parallelity classes. So let L1, L2, Lm be all lines in its fixed parallelity class. We fix some of parallelity classes and look at all lines belonging there. Now, if L is not in this class, that means that L is not parallel to Li's, then L contains M points. So if the M lines in a given parallelity class and L is not there, some other line, then it should necessarily contain m points. How do we show that? Indeed. So if it's not parallel, then it means that for let's see, for I equal to 1, 2, and so on to m, let us look at the intersection. We know that any two lines intersect at exactly one point. Yeah. Also, another thing, the union, observe that the union of all li's, I from 1 to m, is our whole thing P, because this was one of the axioms. So they shouldn't be. Okay, so we're looking at li's L1, L2, and so on. Lm is the set of all lines parallel to each other. I'm saying that, first of all, they're disjoint because they are parallel to each other. And two parallel lines, if they do not coincide, they are disjoint. Also, they should cover the whole P. Why? Because we had this axiom that through any point, there is a line which is not on a given line. There is a line parallel to a given line. So the union should cover the whole thing. And this will imply that the union L equals the union of its intersections with all li's, and that means that L contains m points. There was a question. Okay. So with this important claim, we'll start addressing our main theorem, and it will follow from it fairly easily. Okay, so assume. So we have concluded. So main proof now, finally. So we know that there are at least three parallelity classes. So given our plane, affine plane X, capital X, let say L1, L2, L3 be its arbitrary distinct parallelity classes. We know that they exist, at least three of them. Okay, so assume that L1 contains M1 lines, L2 contains M2 lines, and L3 contains M3 lines. Okay. Yeah. So let's see. So let little L1 belong to capital L1, little L2 to capital L2, and little L3 to capital L3, and say L1 contains N1 points, L2 contains N2 points, So these are notations so far. L3 contains n3 points. Now we'll show that all n's and all m's will coincide. Okay, so the previous claim says then we have that m1 should be equal to n2 should be equal to n3. Why is that? Well, m1 is the number of lines in the class capital L1. L2 and L3 are lines which are not in the class L1. So the number of points, which is denoted by n2 and n3, should be equal to the number of elements in class M1. And if we do the same thing by choosing now L2, capital L2 instead of M1, we'll get M1, and we will be getting N1 equals M2 equals N3. And finally, the last thing would be N1 equals N2 equals N3. As a result, we'll get that all ni's are equal, and they are equal to all mi's. And let us denote this number by n. Okay, so what we get is that every parallelity class should contain n lines, and every line should contain n points. So conclusion, P, which contains n square points. Why? Because in each parallelity class, there are n lines, and each line contains n points, and the union of all lines in a given parallelity class is the whole place. And all these lines are disjoint. Okay, now let's see. What is the next thing to do? So we'll be counting lines which contain a given point. We should prove that every point is contained in n plus 1 lines. Yeah, I think, okay. So we got that we have totally n squared points so far. So the next step would be, so fix some point P in P and align P, align L, which contains P. So let's take another line parallel to P. Parallel to L. So we have such a situation. So we have this point P containing line L and L prime, which is parallel. Now, then for each point on L prime, so there exists a unique line, say, call this point Q maybe. There exists a unique line passing through P and Q. So whatever point Q here we fix, we can find a line like this, because that's the one of the first axioms, that any two distinct points contain a line. So so L prime has n points. Thus, we get L and another n lines passing through P. So totally n plus 1. And the claim is that no other line, there is no other line passing through P. And why is that? Okay, assume that there is. So if this line is parallel to L, then it should coincide with L. If it's not parallel to L, then it should also intersect L prime, or any, if it's not in the class or to which, in the parallelity class to which L and L prime belongs, then it intersects any line in this parallelity class at one point. In particular, it intersects L prime at some point. But then it should say if this point is Q, then it should coincide with the unique line passing through P and Q. So in this way, we have counted all possible lines passing through P, and we know that they're totally n plus 1 such. Okay, now we should finally prove. So we have settled so far that every line has n points, every point is contained in n plus 1 lines, and the total number of points is n squared. The last thing to say is why is it that the total number of lines is n squared plus n. Okay, so now finally, each parallelity class contains n lines, and there are n plus 1 parallelity classes. So we can look at all distinct lines passing through a given point P. They all should necessarily line into distinct parallelity classes. Therefore, the total number of lines is their product. N times n plus 1, which is n squared plus n. Okay, so far so good. I think one should probably take a look at this argument again, but it's not very complicated. It's a little bit lengthy, but not very complicated. Now, the very, very last topic of our course is Latin squares. It's a very nice gadget, tangentially related to affine planes. Latin squared, again, is a classical thing. It was studied from the Middle Ages. A big contribution to this thing has been done by Leonhard Euler in the 16th century, but still there are a whole bunch of open questions in this area as far as I know. Okay, so let me define for you what a Latin square is. So major definition is a Latin square of size n is an n by n matrix with entries 1 through n, such that each row and each column contains all numbers. ones. So once each. So it really looks like a Sudoku. So in each row and each column, you have all numbers from 1 to n repeated once. So let me give you some basic examples. The Latin square of size 2 is, of course, such a thing, for example, or you can switch rows and the columns, but essentially this is the only one. The Latin square of size 3 is 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, sorry, 2, 3. This is a Latin square of size 3. Now, a more systematic example is showing that Latin squares exist for all sizes is as follows. So, for a given integer n big or equal than 2, so organize a matrix. I don't know, call it AN maybe, with the entries so its entries A, I, J would be I plus J mod n. If you do this, you'll get an example of a Latin square. Say, let's do that for size 4. So say n equals to 4. Yeah. So let's do this for size 4. Okay, I plus J mod 4. Okay, so if this is 1, 1, so we should put 2 here, 3. Let's see, it depends whether we use, we should shift it maybe. Mod n, so do we count 0? So let me use labels from 0 to n minus 1 instead of from 1 to n, because that's the only difference. Once we get those, we should shift them. Or maybe we should label it. Okay, anyway. So I'll be using numbers. I'll be using numbers from zero to n minus 1, but then I can shift them by 1. We'll get the same thing. Okay, here we have 3, 0, 1. Now 2 plus 2 is 4, which is 0. 2 plus 3 is 1. Here we have 2. Now here we have 1, 2, 3. And finally here we have 2, 3, 0. So and if you want to get my original notation, I should increase each entry by 1. Then we'll get 3, 4, 1, 2, 4, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 1, for example. Okay, so that's the way one can construct an Latin square of any given size. For Latin squares, it's more important to, the next notion is quite important. This is called, for Latin squares, it's usually you work with pairs of such. 2 Latin squares are called orthogonal. 2 Latin squares are called orthogonal. Okay, So let me call them A and B. If the following holds, so they are of the same size, of size n. So consider pairs of the entries A, I, J, B, I, J. So these are n squared pairs of numbers. And each number is in between 1 to n. Note that there exist exactly n squared. There exist exactly n squared pairs ij. Oops, let me say kl. K is from 1 to n, and l is from 1 to l. Yeah. Okay. If those guys give all pairs of numbers, then A and B are called orthogonal. I'll give you an example so you'll understand what I'm talking about. Okay, this is important to understand. So my A would be 1, 2, 3, 2, 3, 1, 3, 1, 2, and my B would be 1, 2, 3, 3, 1, 2, and 2, 3, 1. So I'm switching the second and the third row in my matrix A to get B. Some claim A and B are orthogonal. So they are Latin squares and they are orthogonal. And what does it mean again? So let's look at all pairs. One entry from A, one entry from B. So A and B give 9 pairs of numbers. So if we look at the place 1, 1, so if we look at here and here, we're getting 1 and 1. Yes. Now if we're looking at here and here, we're getting 2 and 2. If we're looking here and here, we're getting 3 and 3. Now go the second row, 2 and 3. This central element 3, 1. Here 1 and 2. Now the last row 3 and 2. This guy 1 and 3. And finally the last one 2, 1. Now we get 9 pairs of numbers, and they are all possible pairs of numbers you can get where each number belongs to 1 to 3. So one has totally, if we look at all pairs of numbers from 1 to 3, totally, what can we get? We can get 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. These are all possibilities to have pairs of numbers from 1 to 3. And see, in our matrices, we got all of them. So we get this guy here, we get 1, 2 here, we get 1, 3 here, 2, 1 is here, 2, 2 is here, 2, 3 is here, 3, 1 is here, oops, 3, 2 is here, and finally 3, 3 is also around. So if we get all possible n square numbers like this, then we say that the original Latin squares are orthogonal. Okay. Now the next result, which is due to Euler, and it seems to be a fairly complicated proof of that, so we'll take it without a proof. So for any n, there exists at most n minus 1 tuples of pairwise orthogonal Latin squares. So in principle, a given Latin square can be orthogonal to a whole bunch. We're interested in this situation, we're interested in collections of Latin squares of a given size, which are pairwise orthogonal to each other. And Euler has proved in this mid-16th century that for a size n, you can have no more than n plus 1 such guys which pairwise orthogonal to each other. And he also has shown, remark, no pairs of orthogonal Latin squares exist for n equals to 6. So the first interesting case, when we were wondering if there is a affine plane with rank equal to 6, will be related to this result by Euler that no pair of orthogonal Latin squares exist for size n equals to 6. And finally, let me finish with the following statement, which connects affine planes with Latin squares. And with this additional remark, this connection will imply that no affine planes with rank equal to 6 exist. Okay, theorem is as follows. So let X, which is points and lines, be an affine plane with parallelity classes be an affine plane with parallelity classes L0, L1, Ln. Let's see. So let us label L1 by 1, L2 by 2, and so on, Ln by n. This would be our row or column numbers. And let us label, we know that P should contain n squared points, and we identify our points with in P with pairs of numbers 1 to n in the following way, such that we'll call a point small p in capital P will be identified with a pair ij, if P is contained in the nth line, in the ith line of the first class, notes that we have reserved our first class capital L naught and the J
Sorry,
line.
is it big P to small p?
Just 1 second. G's line of L1. Sorry.
Is it big P to small p, or what have you written there?
Okay, so
It's
this
such that
P is a
big P to
point. The
small p.
capital P is the set of points. This is the set of all points. The set of our
Yeah,
points.
I couldn't see the difference in size between them.
Yeah,
Thank
yeah.
you.
Okay. So we'll label a point P by numbers I and J if P is contained in the ith line from the class L0 and the jth line from the class L1. Now, finally, I'll present n-1 tuple of pairwise orthogonal Latin squares, which would be the end of this construction. So finally, for K, so K is 2, 3, and so on, and N, define a matrix AK by, so we're almost done. So the entry Aij of this matrix K would be L if and only if the point the point Ij is contained in the lth line of the class Lk. So this is a construction. It's fairly involved. I wouldn't say that it's completely trivial. So let me just say briefly again, what do we do? So we'll look at parallelity classes. We'll label lines, so there are n+1 of them. We'll label lines in each of them. And now we know that we have n square points, and we label points in our set capital P by pairs I and J, which means a point P is contained in a unique line from L0 and in a unique line from L1. And these are the indices in which lines from L0 and L1 our point is contained. Now, for all classes, so we use the classes L0 and L1 to label our points. Now, for each of the remaining classes, L2, L3, and so on to Ln, we'll be creating an, how it's called, a Latin square matrix by doing the following. So the entry in the place Ij, so we would pick a K, which is 2, 3, and so on to L. And we are saying that the entry Aij of the kth matrix would be L. If this point Ij, it should lie also on some line from the class Lk. If it lies on the Lth line, we're putting an L here. Okay, now the claim is so we're getting A2, A3, and so on, AN are pairwise orthogonal Latin squares. So for each plane, affine plane of rank n, we can get n minus 1 pairwise orthogonal Latin squares with such procedure. And now we get this corollary. No affine plane of rank 6 exists because of this result of Euler's. So he has shown that for size 6, you cannot even find the 2 pairwise orthogonal Latin squares, not to say that you need to get an affine plane of rank 6, you should get 4 such guys, but you cannot even find the 2 of those. This is a connection from finite affine planes to Latin squares, but it's not the same topic. So affine planes is a more rigid object than Latin squares. There, you cannot go back and forth between these two notions. But both of them are quite interesting, important. Affine planes are also used in coding theory a lot, and they are very nice gadgets, in fact, showing in many places. And they are important even, I think, for, how one creates computer codes and safety keys for computers and things like this. Okay, so it's time for me to finish, and I'll see you on Monday. And by Monday, I hope I'll have a better idea what will be on the exam. Okay, so see you on Monday. Bye-bye.